I'm Johanna Rock, and I'm happy to present today the quantized or the work about quantized neural networks for radar interference mitigation. And at this point, I'd also like to say thanks to my co-authors, Wolfgang Roth, Paul Meissner, and Franz Pernkopf. Sorry. So automotive radar is used for driver assistance systems and autonomous driving. The radar sensor itself is used to measure the distance, the velocity, and the angles of objects that are within the environment of the radar sensor. And typically in the automotive context, we use the frequency modulated continuous wave chirp sequence radar type. And in the figure on the right, you can already see a typical scenario where we have multiple cars that are equipped with a radar sensor, and we have multiple objects within the environment of these radar sensors. This could be pedestrians or cyclists, for example. And if we have multiple radar sensors that are sending at the same time, and if they're sending at an overlapping frequency band, this might cause a so-called mutual interference, which means that one radar sensor introduces an interference signal to the other radar sensors. And typical effects that we might have of this kind of interference is an increased noise floor as well as a decreased detection sensitivity. So we can't really detect objects anymore, which can be dangerous. So one crucial part of radar signal processing is the mitigation of such interferences. And here we try to remove the interference from the signal and then increase the detection sensitivity again. There are now two main categories of algorithms that can be used. First, we have the classical and state-of-the-art signal processing algorithms. And then on the other hand, we have maybe 1 year ago, people started to propose to use neural network-based models to perform this task. But there is one huge problem, and I guess every one of you knows what the problem will be. All of these steps have to be run on the hardware directly, so we have very strict requirements for the hardware. So these algorithms have to be performed on that hardware and have to meet these requirements. And in this work, we will focus on memory requirements, because indirectly they influence all the other components, such as the inference speed, but also the energy consumption and computational requirements. And on the right side, you can see an example measurement of such a radar measurement. On the left side, the clean data, and on the right side with simulated interference. And in red, you have indicated the object peaks that should be detected. So the aim of this work is to evaluate CNN-based models for interference mitigation. To do so, we want to use real-world measurements that are mixed with simulated interference. Here we want to show our analysis of the memory requirements of the proposed CNN-based models, and we analyzed effects of binary quantization in terms of architecture and size. Also, we will have a look at quantization strategies, which means that we, on one hand, want to have a look at quantizing or binarizing actually only the weights, then only the activations, and both of them. And finally, we will have a look at multi-bit quantization with exceptionally small base real-valued models. And first, I want to give you a short overview of the range Doppler processing chain. So in the first step, the radar sends out linearly modulated radio frequency chirps, or also called ramps, and the objects then reflect this signal, and the signal is then perceived by one or multiple antennas and mixed with the transmit signal, and this gives us the so-called intermediate frequency, or IF signal, and this is indicated in yellow in the bottom of the figure. And in the simulated case, such a signal could look like this in the time domain. So it consists of the object reflections as well as the noise, for example, from the receiver. And then in the next step, a discrete Fourier transform is performed over all the n fast time samples for each of the m ramps. And in the image, you can see such a simulated signal And we have peaks at the positions where we have objects within the radar's environment. In the next step, another DFT is performed, this time over the MRAMs for each of the fast time samplers, and this gives us the so-called range Doppler map, which will be the basis for our interference mitigation. And this complex spectrum contains peaks at the positions where the velocity and the distance intersect of the objects that are within the radar's environment. Then there might be, or there always is, an object detection step where we try to find the most prominent peaks that most likely correspond to real objects rather than noise or clutter in the range Doppler map. And then there might be an angle estimation step where another DFT is performed over several antennas, which then gives us the angle estimation or the physical position of objects. And then there might be some further processing steps such as sensor fusion, object classification, and motion estimation. Classical interference mitigation can be applied either to time domain or to the frequency domain signal after the first DFT. While CNN-based interference mitigation is typically performed after the first DFT or the second DFT on the range Doppler map, which is what we will be doing, because in our case, this simply performs best. As for the CNN model that we are using, it's a fully convolutional approach with 3x3 kernels in the convolution. We use batch normalization and the value activation function. As inputs for the CNN, we use the measurements that are mixed with interference, and as the targets, we use only the measurements without the interference. Note that the inputs and the outputs are in general complex spectra, so we use two channels of the CNN in order to represent the real and the imaginary parts of this complex range Doppler spectra. Also, we don't use any pooling operations, and we use zero same padding, which means that the spatial dimension of the inputs, the outputs, and all the activations is the same. As for quantization, we use the quantization over training with the straight-through gradient estimator. So in general, the problem with training quantized neural networks is that the quantization functions or the piecewise constant activation functions introduce zero gradients during backpropagation, which means that we can't use typical gradient-based optimization algorithms anymore. So the solution here, or the idea behind this approach, is to approximate the gradients during the backward pass. And we want to approximate these gradients with the gradients of other functions that have a similar function shape or that are the identity. F of x equals x, which means that we just pass on the gradients from earlier or from lower components of the computational graph to higher components. And in practice, this works very well, which is why it is used very often. And here you can see a simplified computation graph of a convolutional layer. So during the forward pass, we follow the purple line over here. So the real valued weights, which you can see over here, are quantized with the quantization function. And then we get the discrete valued weights, which are used for the convolution operation with the layers input. And then in the next step, the sign activation function is applied and we get the inputs for the next layer. And then during the backward pass, we try to avoid these piecewise constant functions because they will yield zero gradients. And instead we follow the green dashed line and take the gradients of similarly shaped functions, such as the 10H for sign, or as the identity over here for the quantization function. And then the gradient updates are applied to real valued weights as normal. As for the data set, we used, or we took the measurements in inner city traffic scenarios. We took around 850 measurements with multiple radar snapshots and antennas each. These measurements contain extended object, which means that we have object peak clusters rather than single peaks on one range Doppler cell. And also we have some very strong biases in the data, such as the ego velocity of the measurement vehicle and the equipment reflections. The interference is simulated and added to the time domain measurement signal as in the equation given up below. And on the right side, you can see an example for such a measurement. So in the bottom, we have the camera reference image. And here in the red circle, you can see a car that is departing from the measurement vehicle. And at the top, you can see the range Doppler map without interference. And we can see that the car is already around 45 meters away and is driving away from the measurement vehicle with around 8 meters per second. And in the range Doppler map with interference, which is a quite strong interference in this case, we can't see this object at all, but we can only see the very close and strongly reflecting objects over here. As for the evaluation, we use the F1 score. It's the geometric mean of precision and recall. And in order to calculate this, we took the clean measurements. We manually labeled all object peaks, which gives us the ground truth peak locations. And then as for the CNN processed range Doppler maps, we used the cell averaging C for peak detector in order to automatically detect all the peaks in the range Doppler map, which is then, together with the ground truth peak locations, the basis for the F1 score. Here, I would like to give you an overview of our findings about the memory requirements of these CNN models for the interference mitigation task during inference. So we know that the model during the inference step, it needs memory to store the weights, and it needs memory to store temporary values for the calculations of the convolution operation, which we call the activations. So on the left side, we have models with a small number of channels, and on the right side, we have models with a large number of channels. And also note the different scale of the axis here and here. We can see that models with a small number of channels are much smaller than models with a large number of channels, which isn't really surprising. But what is interesting is that these very small models on the left side here, they require almost all the memory for storing the activations and not for the weights. So we recap, the quantization reduces memory by a factor of up to 32, which is in the binary case, which means that we really need small models as base models for quantization in order to reach the overall smallest model that we can find. And then also for these very small real-valued models, we know that the memory for activations is kind of more important than the memory for weights. So also for quantization, we have to focus on the activations. And here we have the performance to memory relation of binary quantization. On the x-axis, we have the memory in a logarithmic scale. It's given in megabytes. And on the y-axis, we have the F1 score, which is our performance. So the higher, the better. And as reference, we have the F1 score of the clean and the interfered data with the blue and orange lines. And we have three categories of binarized models. First, we have the real valued model for weights and activations in green. And then we have the binarized weights with real valued activations in red. And then the binary activations with real valued weights in purple. And note that if we try to make both the weights and the activations binary numbers, this doesn't work for our task, so it's not included in this plot. And here we can already see that all the Pareto optimal points are actually very small real valued models. We conclude that binarized CNNs are not effective for memory reduction in our case. But please note, and we've already heard this already, this is not the case for other tasks, such as, for example, classification tasks. And it also really depends on the model, because larger, highly overparameterized models actually do work quite well also in the binary case. Now we want to show the quantization with multiple bit widths, because this indeed does work for our case and our task. So what we tried is we used quantization with 1, 2, 4, 6, 8, and the real value case with 32 bits for the weights and the activations alike. And we can see that 1 or 2 bits are not enough in order to solve this interference mitigation task, but with 4 bits and more, we are already able to increase the F1 score compared to the data with interference. And if we use 8 bits for weights and activations, we already reach a very similar F1 score than the real valued model. So here the same results, but in numbers, we see we have a very similar F1 score. And also we can see that the memory reduction compared to the real valued case is around 75%. And this gives us a model with around 280 kilobytes, which is really, really small and does fit onto a radar sensor. So in summary, we can say that small real valued models are required as base models for quantization. And we've seen that especially for these models, it's more important to focus on quantizing the activations rather than the weights. We've also seen that binarized small CNN models are not effective for memory reduction for our considered task. And we used multi-bit quantization and managed to retain the F1 score with 8 bits and more. And with a quantization of 8 bits for weights and activation, this means we have a 75% reduction of overall memory. And we get the model with 280 kilobytes, which is great good, I think. Yeah, so thank you for listening. And if you have any questions, I'm happy to answer them.
Many thanks for the presentation on this particular study on a rather unconventional application in terms of quantization. Are there questions from the audience?
Maybe one question.
Yeah, sure.
You pretty much already answered most of my question. And you said that the fact that small models don't really work as well, small original models, that's something that's special to your case. Because what we experience is actually the opposite. Can you tell a little bit more about why you think that is?
What exactly do you mean?
Why it's special for your case?
I mean, I think special for my case, I mean, I have a regression task here. So I think it's not that easy to quantize to very small bit numbers. So I think for a regression task, just if you think about it numerically, you can't just represent everything you want to. So I think this is why in my case, it's really hard to quantize to binary weights or activations, or especially to activations, which you can see already here, because these are always the kind of the same models, but then quantized. So we can see that we need bigger original models in order to have a stronger quantization. But I think this just comes because then the network is kind of learning to split the information onto different channels, for example. Mm-hmm. But this is not really confirmed. This is just what I think why this might be happening. But I mean, in general, if you have larger models, they can, of course, represent more data and also propagate more data. So you can reduce the bit size even more than if you have very small models, I think.
Yeah, just have a bigger information flow to start with.
And the other funny thing for me is that, well, the funny thing for me is it's again 8 bits as a sweet spot. So I don't know why, but all the time when talking about quantization, it is 8 bits, which as a matter of fact, and possibly by accident, is also something which is super in line with most computer architectures out there. Mm-hmm. Any other questions from the audience?
So you mentioned you didn't use pooling. Did you experiment with that, or did you just not touch that at all?
I did experiment with this in the beginning. Actually, for this paper, I didn't, because I already knew that it wouldn't work that well. But the reason why is also because we have a regression task and we don't want to lose the how do you say, the precision of the object peaks. So I think you can kind of do this if you have some kind of unit-shaped network, and then you have the up convolutions again in order to restore the information from earlier layers. Because I mean, the main problem is the input and the output has the same spatial dimension. So if I just use pooling, this kind of groups my information of the inputs spatially together. So I would have to have some kind of up convolution somewhere in the network in order to recreate this kind of information, the spatial information, because it just gets lost through the pooling operation. And I think this might very well work, but you would result in larger models. So this is why we didn't do it. And it works quite well without. So I think simpler is always the better option.
Okay, thank you.
I would like to.
Any other questions? Sorry.
For your model, when you're using the real valued model, then you use the ReLO activation function, right?
Mm-hmm.
And for the quantized one, you use the sign function, right?
Exactly, yeah.
Did you try to use to train a model with real valued sign activation? Because I think this could also already increase the performance, reduce the performance quite far.
Sorry, with real valued sign?
Oh no, like a sigmoid function or
okay.
something that is similar to a sign function.
Yeah, actually for the real valued case, we tried a lot of activation functions and ReLO turned out to be the best one. But I think sigmoid also worked well, but I don't remember exactly. But overall, ReLO was the better one. But yeah, for the binary case, we just used the sign activation function because
okay, yeah,
it was the simplest option.
What I was trying to say is maybe a different approximation, like a clipped ReLO would have worked better.
Mm-hmm. Okay, yeah, this could very well be, but we didn't try this actually. Yeah.
Thank you.
So if there are no more questions, which apparently is not the case, then many thanks for the presentation. And a reminder that there's more than just classification out there, which possibly has some impact on the quantization too. So thanks again for the presentation.